Today's problem is nearest smaller element, difficulty easy. This is part of Interview Bit's 12-week interview preparation kit. So pause the video, go over to Interview Bit, try the problem, and then come back and we'll walk through it. All right, let's see. This is asked at Amazon, Microsoft. Given an array, find the nearest smaller element for, well, G of I. G, I guess, is going to be the output array. Yeah, G is the output array. Find the nearest smallest element, G of I, for every element A of I in the array such that the element has an index smaller than I. Okay. More formally, G at I for an element A at I is an element A at J such that J is the maximum possible and J is less than I. J is less than I, but it's as close to I as it can be. And A at J is less than A at I. So, yeah, the element at J is less than the element at I. Elements for which no smaller element exists, consider the next smaller element as -1. So that's the default if there is no smaller element. And then we're talking about the nearest smaller element to the right, I'm sorry, not to the right, to the left of each element in the input array. All right, elements, there's no smaller element. The only argument given, blah, blah, blah. All right, yeah, so let's look at how this would work. Well, let's look at it once just by way of understanding it, and then we'll look at the algorithm. So first of all, we've got let me get a pen here. We've got A 4. Now, there is no element to the left of 4, so there is no smaller element to the left of 4, so we've got to put -1 there as the output. The next element, 5. Closest smaller element to the left is 4. Next, 2. There are no elements smaller than 2 to the left of 2, so again, we've got to go -1. 10. Smallest element to the left of 10 is 2. 8, smallest element to the left of 8 is 2. I think I'm not saying that exactly right. Smallest element to, but the nearest smaller element to 10 is 2. The nearest smaller element to 8 is also 2. All right. So let's look at the algorithm. This problem is solved with a stack, or specifically what's called a monotonic stack. A monotonic stack means that the elements on the stack only go in one direction. Either they go from greater to smaller, or they go from smaller to greater. In this case, it's monotonic. Let me think. Smaller to greater. So we don't push any element on the stack on top of a larger element, larger number. All right, so we're going to have to define a couple of data structures here. One is the result, which is an integer list. Basically, that would be this, G, the output, and then a stack. Now, there is a stack data structure in Java, but it's considered more of a legacy data structure. And now we typically use a deck to implement stacks. A deck is an interface, so the class is arrayDeck. So we usually define stacks like this. All right, and then we iterate through the array. So let's try that. Num at A. So we'll start here with the 4. While stack is not empty. Actually, the stack is empty right now. So we'll just drop through that while loop. If the stack is empty, then result add -1. So if the stack is empty, that means there is nothing to the left of this number that is smaller. So we put the -1 right here. Okay, and then we can push the number on the stack, the 4. That's going to go right here. All right, next, num is 5. While the stack is not empty and stack peak is greater than or equal to num, well, 4 is not greater than or equal to 5. So we'll drop through the while loop. If stack is empty, it's not. Else, result add stack dot peak, and the peak would be the 4. So whatever element is on the top of the stack, that is going to be the smaller element, the closest smaller element to the left, and then push the 5. Okay. Next number, 2. We'll go through here. While the stack is not empty and stack peak is greater than or equal to num, which it is. Its stack peak is 5, and that is greater than or equal to 2. Again, this is a monotonic stack, so we're not going to push the 2 on the 5. So we'll pop the 5. Gone. Stack is still not empty, and stack peak, which is now 4, is still greater than or equal to 2. So pop it again. Now the stack is not empty, so we drop through the while loop. If the stack is empty, add -1 right here. There are no numbers to the left of 2 that are smaller than 2. And push the number 2. Go back up, grab the next number. Next number is 10. Stack is not empty. 2 is not greater than or equal to 10. So we get down here, stack not empty, else result, add stack peak. That means that 2 is the next smaller element to 10. And push the 10. Okay. Next number, 8. Stack is not empty. Stack peak is greater than or equal to num. We got to pop it again. We don't put smaller numbers on bigger numbers in this stack. That's the definition of it. A monotonic stack. It only goes in one direction. So the 10 is gone. Stack is empty. Stack is not empty. Stack peak is not 2 is not greater than or equal to 8. So stack is not empty. Result add stack peak. Again, it's a 2. Stack push. Okay, we can push the 8. There's nothing left in A. We are done. We have the output. We return it, and that's it. So this is a monotonic stack problem. Not uncommon that you will encounter these in an interview. All right, thanks for watching. If you found this helpful, give it a like, subscribe. Check out the playlist on the screen to keep improving your interview skills. The video description and the pinned comment both have links to more resources, including a free LeetCode patterns cheat sheet, which is downloadable immediately. It includes the monotonic stack pattern. And there's a link to Code and Conquer, which is my complete coding interview prep course. And we'll see you next time. I just went through the whole video and stopped it, and I realized I didn't even run the solution. Let's run the solution. All right. I can't run with that. All right, here we go. Easy success, hard success, total success. All right. That's good. Everything I said before still stands, and again, we'll see you next time.